Hello everyone, welcome back. We were dealing with Crocos theorem and I said that I will get back to you on examples in this class. We defined the full governing equation or a full equation for Crocos theorem as this. I have such a case. Now, if I look at different things, even if I have isentropic flow and isenthalpic flow, if my velocity is changing in time, I may produce vorticity due to that. That is one more thing I can see from here. Okay? Even if I increase velocity even isentropically, I am going to have a case where I will have vorticity produced. Okay? That is one more statement from Crocos theorem. Now, we will see some examples. Say I have supersonic flow over a blunt body. Okay. What am I starting with? I am starting with, let us say, two streamlines like this. One streamline very close to the center line will go like this, and the other one is going to have immediate deflection and then it is going to go like this. This is the flow field we have. If I label them as 1 and 2, I am of course starting with the same enthalpy in both of them, same stagnation enthalpy in both of them. Free stream condition is the same for both. So, I am having no gradient difference, and since that particular stream tube with this streamline in it is going to be having no change in enthalpy, stagnation enthalpy, because it is adiabatic flow. This flow through a shock is adiabatic anyway, that is the only difference in this. Okay, it is just going through that particular process. Here this particular stream tube around this streamline also will be H naught does not change along the streamline. So, I am going to say H naught here is same as H naught here. Okay. That means in this region if I look at it, I am going to have del H naught 0. Okay. Gradient in H naught here is 0, it is all same H naught. Assuming I am having adiabatic wall here, okay, I am assuming my model whatever I am putting here is adiabatic. It need not be the case in real life. If there is an aircraft going supersonic, it may have some heat transfer in also. We will neglect that for now. If I think of such a case, then I am having a condition, and I say it is a steady problem, I will neglect this dou u by dou t term also. So, whatever I have, the right hand side is 0, but now I can say that entropy on the top layer is different from entropy on this layer. Which one is higher? 1 is higher or 2 is higher? Center line 1 is higher. Okay. If 1 is higher, why is 1 higher? This is a normal shock, very strong shock, while this one is less strong shock, it is more oblique. Okay. As I go away from center, entropy will be decreasing lesser and less. And when I go far out, somewhere out there, it will become Mach wave, where entropy does not change at all. That can also happen. So, entropy change decreases as I go there. So, which entropy is higher after the shock condition? Is it 1 or 2? Which one is higher? We talked about entropy jump is higher. Which one is higher at the end when I look at here? After shock condition, I want to apply this equation. So, what will be the condition? Let us say entropy initially is whatever, 1 joule per Kelvin or whatever, some unit. Here it is jumping higher value, here it is jumping lesser value. What will be the final thing? Which one will be higher? Simple enough, right? Nobody is thinking? Great. I will just tell you one will be higher. Why? We start with the same value, this one increased more than that one. So, this will be higher value compared to that value, that is all. Okay. Now, if this is the case, what is my del S? What will be my del S? Will it be positive, negative? So, it is going to have a dou by dou x term and a dou by dou y term. Let us assume that the change in x is very negligible, we will just look at y term. What will that be? Dou by dou y term. What will it be? Dou s by dou y. As y increases, s decreases. So it is going to be less than 0. Okay. Right hand side of my equation is both these terms are 0. I told it is a steady problem and isoenthalpic problem. Okay. So I am going to have only this particular part, and in here I found that this is negative, which means this term should be positive. Okay. What is the kind of vorticity I am developing? I have to match all these together. That is all I am thinking. Okay. What is the kind of vorticity I am developing? This is higher velocity and is going there. This is very, very low velocity. Overall, I am developing vorticity like this into the board. Okay. While my x and y coordinates are like this, right? X, y is like this. So I am developing, z will be out like this, right-handed coordinate system. This is my positive and vorticity del cross v, but I am producing this. Okay. So I am going to have del cross u negative. Del cross u is negative, and I want to do u cross that. U cross that will be like this. Okay. So I am finally getting that term to be positive. Okay. So I am finally having u cross del cross u greater than 0. So now I am finding everything is matching. So I am now going to say this is the reason why I am getting a vorticity that is like this in this flow. Okay. That is what is finally happening in there. Okay. This is one example. I can go through this whole example for different cases. I won't go into details of the other ones. I will just tell you I can have a Mach reflection at a wall of an oblique shock. What is going to happen here? There will be a slip line like this. What do you mean by slip line? We said there is no viscosity, so there is slip line. But now if we add viscosity, then there is going to be a small shear layer sitting here. What is happening inside there? It is having vorticity. If there is a slip, that means there is a gradient in velocity, right? Which one will go higher? Which one will have higher velocity? Upper one will have higher velocity. So I am again going to have negative vorticity. I can go through the same explanation, it will give you the exact same answer finally. Okay. You can go through this problem also and get yourself convinced. I can now think about a more crazy example. One weak oblique shock and a very, very high beta oblique shock. I don't want to call it strong oblique shock. Both are weak oblique shock if you think about strong versus weak. But one is a weak angle, one is a high angle oblique shock. If they cross, what does this mean? This was probably produced by a wedge that is like this. This was produced by a wedge that is more like this. Right? What will be the final direction? On an average, I will draw a symmetry line somewhere like this. Right? So the final direction will be something like this. Of course, I don't have any wedge like this very close to my flow field. Finally, it is going to look something like this. This is my flow field finally. I have incoming flow. It is turned and it is going like this. Here this is my same incoming flow. Same incoming flow, it turned more and finally it turned like this. If I think of this particular case also, I can now show that this line will have vorticity across. Why? I am having different entropies across these streamlines, across these two lines. Everywhere else it is processed by the same shock. If I pick one streamline here and one streamline here, exactly same entropy. Del S will be 0 there. Del H is also 0, it is a steady, so there is no vorticity there. Okay, every term in this will go to 0. If I go across this line, they are processed by different set of shocks. So only across this line there will be vorticity. Only on the line there will be vorticity finally. Because across this line there is del H naught 0, dou u by dou t is 0, but del S is not 0. Because of that there will be vorticity produced. Okay. I have picked a problem, again it is going to give the same kind of vorticity. Okay, if I picked the top one as very strong, it will be the other way vorticity, but I did not pick that. Okay. Anyways. So that ends the discussion on our Crocco theorem. Is just to introduce that there is a mechanism by which we can prove that there is vorticity in a slip line. That is all I just gave now. Okay, we won't worry about this anymore. We will just move on to adiabatic flow in a duct with friction present. I am saying adiabatic flow in a duct because I can solve a problem for isothermal flow in a duct, where the temperature of the wall is fixed or the temperature of the gas is fixed. I can work on any particular way where there is heat transfer allowed. We will currently work with a situation where there is no heat transfer into or out of the gas. Okay. Whatever enthalpy the gas has, stagnation enthalpy, it stays the same. Okay. That is one thing, and this is one problem where we are going to say viscosity is present. The only other problem where we discussed viscosity was present was shear layer. After that, it is this one. In the middle, we discussed the energy equation, and we know that because there is viscosity present, we may have entropy production, and because there is heat transfer, there may be entropy production. Now we said adiabatic, so there is no heat transfer into the gas. So there is only one way of producing entropy, that is viscous forces. Okay. That is all you are going to have currently. That is coming from your discussion on energy equation and entropy equation. Okay, that was already done last class. Okay. So now when we look at ordinary flow fields, typically we did this flow through a nozzle or flow of a jet. In all those problems, we do not consider viscosity as much, and I told you there is a special case in a jet flow where there is the boundary will slowly have shear layer developing and it will slowly eat into the main flow. Other than that, we did not use viscosity anywhere. Okay. So is that really valid? If it is not valid, it will not be in books. Okay. It so happens that for most common applications, it works very well. Okay. I am just going to say, yes, I can live with not using viscosity all the time, okay, because simply because the inertial momentum or the forces, inertial forces involved are way high compared to my viscous forces that I am having in my flow systems. Okay. Viscous force or the friction force is really small, and it happens only at some corner of my flow where the fluid interacts with the wall typically. Okay. That I will start neglecting this in my overall bulk, assuming that my bulk flow cross section area is much more than the viscous interaction area, which will typically be very small if my flow duct is big in size. When my flow duct becomes smaller and smaller in size, they become comparable. You will see that immediately after we derive the whole thing. There is a particular term called hydraulic diameter that will take into effect all these parameters naturally. Okay. Were we justified in not using friction in a nozzle flow? In a way, yes, but if you want to do more accurate results, you still have to use that also in there. Friction with area change is the actual problem I have to study if there is a flow through a nozzle. And if it is a heated wall, then I have to consider heat transfer also along with it. We will ignore all that currently. We will just say in a nozzle flow, we will ignore heat transfer or friction. That is the simplest way to solve it, which we did already. Okay. But if I consider any duct, even if it is a straight line duct, just constant area duct, if I have flow for long enough distances, the net integral force I am generating through this whole duct against the flow will be high if the length of the duct is high. Okay. For any small distance, if I consider, the net force produced by friction will be very small, but if my length of the duct is very long, then slowly the integral of all the forces on the fluid totally over all the wall surfaces due to friction is eventually going to win over my other forces, pressure force or inertial force or everything else. Okay. So typically we will start using friction only when the duct lengths are somewhat long. How long is long? It depends on the flow problem specifically. We will go to numerical examples later and you will emphasize that fact later. Okay. As of now, if I am going to say I have a flow field like this, okay, very common, we will go deal with it later. A very common flow field like this, I am going to say for this nozzle like shape up to here, I will neglect friction, and this nozzle like shape here I will neglect friction, and this intermediate region which is very long I will consider friction. Okay. Typically this is the simplest way to include friction, very easy to do this one compared to friction along with area variation in this particular case. I am more justified in saying friction is neglected here than this one, because the area variation is slow and it takes long time. This length is not very small. Okay. So you have to think about that also. You may not be always very well valid assumption. Okay. Sometimes it may not be very good. And we are going to deal with, in this particular course, only constant area duct. I will probably outline how to deal with the whole thing in a generalized notation later, but just a constant area duct we are going to deal with right now. Okay. This particular problem was first formulated by I believe his name is Gino Fano. Okay. Anyway, some G Fano. Okay. G Fano, I think it is Gino, Gino. Okay. It's an Italian engineer, okay, who did this for the first time. He did not get recognition for his work till he died. That's all I know about him. Okay. He did not know that he is going to become famous. Okay. So anyways, this particular flow field is called Fano flow, okay, commonly referred to as Fano flow. What are the assumptions? I am going to say it is a constant area duct, steady 1D perfect gas flow in a adiabatic condition. Okay. These are the assumptions in constant area adiabatic duct. Steady 1D perfect gas flow in constant area adiabatic duct with no body force or mass addition. I gave you, I believe, 7 different assumptions involved. Okay. This is the overall way to look at this problem. Basically, if I look at all the terms in my conservation equations, you will see all of these terms coming up. Okay. Now, with all these assumptions, since I said steady 1D, I can immediately go and use all my steady 1D equations which we derived for any generalized flow before. So I will start from there, I won't derive everything from scratch. I am going to have mass equation which we already have as rho a u equal to constant. In this case, area is a constant, so I can pull it out and say rho u is a constant. That is the only special thing if I want to think about it. Okay. Rho a u is also m dot, mass flow rate. Okay. So I can rewrite this as rho u is a constant, the constant is equal to m dot by a, which we know is a constant anyway. Now from here, of course, you can immediately go to the thin control volume. You remember we did 2 types of control volume, a big one and a thin control volume, where you can just think about small changes. It will come out to be differential form. The differential form will be d rho by rho plus du by u equal to 0. You can go and do it, or you can, we did this long back and just go look at it and say that will have a dA by a also along with it, and area does not change, so dA is 0, then you will end up with this. That is another way of looking at the same thing. You can derive it, it is not very difficult to derive. Mass equation is the easiest to derive everywhere. Okay. Now we will go for momentum equation. Okay. Now I want to draw this small figure here. I will pick this small zone. This is my thin control volume way of looking at things. I am going to say there is frictional force, tau is the wall shear stress. Of course, I have to multiply this with the area of contact to get the actual force, and I am having a pressure P here and a pressure P plus dP here, and the whole flow is having a velocity here, and this is going to have a u plus du here. So you want to study this whole thing, and of course it has a density rho here and rho plus d rho there. If I think about the whole thing, I will finally I won't go into the detail again. I just have to tell that I am adding one more factor here, which is P into A minus P plus dP into A minus tau wall into area of contact is the perimeter of the duct times the thickness of the slice I am using. Okay. So it will be perimeter into, I will use as dx currently. These are the net forces that are acting on my fluid element inside that small control volume. Okay. Now this is going to cause the net acceleration. I know my mass flow rate is constant. Okay. So the acceleration is going to be mass flow rate times the velocity. I can think of that as one way of looking at momentum. So I can now say this is equal to rho ua into u plus du. Of course, I should actually think about rho plus du and all, but that rho plus d rho into u plus du is going to be same as rho u. That's coming from mass equation. So I will just use rho ua here, okay, minus rho ua times u. Okay. This is going to be my conservation form. I will just convert this to differential form. We will just simplify to I want to use P for perimeter, but P is pressure, so I will just keep writing perimeter full all the time. Eventually we won't need it, we will remove it in 2-3 lines. Okay. We will have this particular form. I see that A is present in 2 of these terms. I will divide by A, so then A will go to below the perimeter. Okay. Maybe I will introduce it right here. We will define something called a hydraulic diameter. Okay. Hydraulic diameter, which is defined as 4 times perimeter divided by area. When I say area, it is the cross section area available for the flow. Okay. 4 times perimeter by cross section area, that is what I am going to have. Okay. How do we get to this 4? This is the engineering way of looking at things. Not all ducts will have circular duct, right? Not all will have circular cross section. So engineers used this and finally found that if I use this formula, I will get diameter for my circular duct naturally, and if it is a square duct, I will get the side of that square. Okay. Just see that directly. If I put 4 into pi r square divided, that is my area of circle, right? Pi r square. Sorry, I used area on the top. I did something wrong. I am having wrong units, right? It should be 4 into area by perimeter. Yeah, I am having wrong units because of that. Perimeter in the denominator. Perimeter here. That is why I am going wrong here. Oh yeah, pi r square is correct. Yeah. Divided by perimeter, okay, which will be 2 pi r for a circle. This is going to give me 2r, which is my diameter of my circle. Okay. That comes out to be right. If I take a square cross section, then I am going to have 4 into some area, some side is a, let us say 4 into a square divided by 4a. So it is going to give me a. So if I think of a square cross section, this is my hydraulic diameter. If I think of a circle cross section, this is my hydraulic diameter. This is how they defined hydraulic diameter. That is why you have this 4. Just remember that, then you will never go wrong in this formula. The mistake I made should never happen because it should have dimensions of meter. I had a perimeter by area, that will have 1 by meter as dimension. That can never happen. Okay. So simple checks, always keep in mind, you are all basic engineers. Okay. So now I will use this inside here when I divide this expression by a. I am having perimeter by area. Okay. Perimeter by area is 1 by dh. Okay. Just remember that. We will start using that. Actually, perimeter by area is 4 by dh, not 1 by dh. Okay. So if I substitute that, I will end up with minus dp minus tau wall 4 dx by dh is equal to rho u du. Okay. I will end up with this particular form. I want to write it similar to what we did in mass equation, du by u kind of form I want to write. Okay. So I want to write it such that it becomes du by u. So what should I do to make it du by u? Divide by rho u square. Okay. Divide by rho u square the whole thing. I can end up with minus dp by rho u square minus tau wall by rho u square into 4 dx by dh equal to du by u. Okay. This is the situation I have. I divided by rho u square. Can any of those terms be 0? You keep checking with this. Okay. If there is flow, u cannot be 0, okay, and density can never go to 0, okay, assuming continuum, that is. Okay. So, you keep checking it when you are dividing something for the whole equation. You should always make sure you are not dividing by 0 ever. If you divide by 0, math does not hold anymore. Do not ever do that. It can never be 0 any continuous situation. That is what you have to think about. Okay. We will keep it this particular form. We will come back to this later. I will start using this after some time. Okay. This is our momentum equation. Now I will go for energy. Energy equation, of course, it is h naught equal to constant. Okay, we said it is adiabatic, so it is h naught equal to constant. Cpt plus u square by 2 equal to constant. Okay, that is what I have, which means this is equal to Cp into t plus dt plus u plus du square by 2 is equal to that also. From this part and the last part, I can get some relation for dt by t, etc. So, we will start taking this and the last part and comparing the terms. We will see what is remaining. What is remaining will be Cp dt plus u du plus du whole square by 2. These are the only terms that is remaining. So, this will be equal to 0. This is what I have. Now, I will say du is so small that du square can be neglected compared to all the other terms. This is a standard thing we keep doing with the differential form. Okay, this is a standard calculus trick. Now, I want to write this as dt by t, similar to du by u. I will write this as dt by t. So, when I write it as dt by t, I divide this whole equation by t, okay, and I will write Cp as, in terms of r, what will it be? Gamma r by gamma minus 1. I will put a t below now. I have divided this term by t plus I have this particular form, but I want this to be du by u. So, what will I do? I will put u square and a u at the bottom. Okay, that is same as just u on the top. Okay, I have this particular form. We want to rearrange this further. If I think about taking this r to the denominator, I will divide this whole thing by gamma r. Okay. Let us say I multiply and divide by gamma r here. I am doing the whole thing in one equation. I want to make it look good finally, that is all. Okay. So, if I do that, I can now say that this gamma r can never be 0 and just cancel this. Gamma r is a common factor out of this, that cannot be 0, only the remaining term is 0. So, I will finally end up with dt by t plus gamma minus 1 times m square. How did I get m square? Gamma r t is a square, u square by a square I have, times du by u equal to 0. Okay. Now, I have a relation between dt by t and du by u. This is one thing I have. We will come back to du by u and dx later. We already have from mass equation d rho by rho and du by u. Those are the things we have as of now. Now, next I want to go look at state equation and get a dp by p. So, as of now I used mass, momentum, energy. Now, I am going for state equation. P equal to rho r t. If P equal to rho r t, dP equal to d rho r t plus rho r dt, right, just differentiation by parts. Okay. Now, I will divide this by P because I want dP by P. where I use P equal to rho RT here. So, I will divide this d rho RT by rho RT, I will get d rho by rho. Again this will become dt by T. This is another relation I have. Okay. Now, if I substitute this d rho by rho from mass equation, what will I have? Minus du by u I will have. Okay. And I am going to substitute dt by T from energy equation in terms of du by u. So, I will finally end up with dp by P equal to minus du by u, and then I will use dt by T from there, that will be a minus gamma minus 1 m square du by u. Okay. This is the expression I finally get. So, I will pull out du by u common, minus du by u common, I will have 1 plus gamma minus 1 m square. Okay. That is the expression I have. This is dp by P. So, now I have dt by T in terms of du by u, d rho by rho in terms of du by u, dp by P in terms of du by u, but suddenly dp by P has a m inside and dt by T also has a m inside. I do not know how m varies with u. Let us find that out next. What do we have? M equal to u by square root of gamma RT. Okay. So, now I can tell that I will just go a little faster, dm by m equal to du by u minus 1 by 2 dt by T. I am assuming you can do that one more intermediate step, just differentiate this and divide by m, you can do that, you will get to this particular form. Okay. Now, I will substitute my dt by T in terms of du by u here. Okay. So, I am going to have du by u pulled out common 1 minus half times dt by T will be minus gamma minus 1 m square times du by u. This and this will get cancelled, it will become plus. This is the term I have. Okay. Now, if I look at it, 1 plus gamma minus 1 by 2 m square you are getting. Okay. So, dm by m equal to du by u into 1 plus gamma minus 1 by 2 m square. This is the next term you are having. Okay. Now, if I think about it, for a given du, I can get a dm. Now, I can get every other variable p, rho, t, everything I can get if I know what is the change in velocity. I have to think about one more thing, entropy, because some of the changes may not be allowed. We need to have ds greater than 0. So, now I want to find ds by s in terms of du by u. Okay. That is the next term we want to do. Actually, ds in terms of du by u is also fine. You want ds in terms of du by u. How do I go there? We know ds, I have to put entropy here. Okay. Entropy ds is equal to, we have so many forms, I will write a form that is convenient for me. Cp dt minus r dp by P. Okay, actually, it should be dt by T. Okay. I will write it like this. You can bring it to this particular form. Okay. This is how you get the isentropic relations. Remember, long time back we did pressure to temperature isentropic relation. We got to this form, and this when you integrate and put ds equal to delta s equal to 0, you get to that particular relation between P and T. Okay, that is sitting here. So, I will start from this particular relation. Now, what should I do? I want to get everything in terms of du by u. Start substituting everything else inside here. So, Cp in terms of r I will expand, gamma r by gamma minus 1 times dt by T in terms of du by u will be minus gamma minus 1 m square du by u. I put a minus in front of this bracket now. Okay. And I have a minus r dp by P. dp by P we already have an expression, there is a minus there, so I will make it plus du by u times 1 plus gamma minus 1, there is no by 2 here, gamma minus 1 times m square. This is the expression I get from here. Now if you look at this particular term, gamma minus 1 gets cancelled. Okay. So if I look at the remaining terms, I will bunch out common terms. R times du by u is common. Look at the remaining terms, there is a minus gamma r m square, minus gamma r m square is remaining, and then I look at here, I pulled out r du by u, so remaining thing is plus 1 plus, oh r cannot be inside, right? I pulled out r already, sorry, r I pulled out already here. So it is minus gamma m square plus 1 plus gamma minus 1 m square. This is what I have. If I look at it, minus gamma m square plus gamma m square will get cancelled. Okay, it looks like this is one term, actually this is just one term and I have cancelled that term. So the remaining thing is 1 minus m square, that is the only thing left. So this is equal to 1 minus m square times r du by u. Okay, very important result. From now on it is simple. I just have to find what is going to happen with each variable. Simple thing to do. I have, I will write it again here, ds equal to 1 minus m square times r du by u. So suddenly we are seeing ds switches sign across m equal to 1. Okay, very important thing. Okay. So now let us consider a case du greater than 0. If m is less than 1, then I will have ds less than 0. M greater than 1 implies ds greater than 0. This is what I am saying. Okay. So the top case is not allowed, this one is allowed. We know only cases where entropy increases will be allowed in nature. So I am going that direction. Okay. And similarly, if we look at du less than 0, if du is equal to 0, all that d delta d terms will all be 0. Okay, d rho by rho will be 0, dt by t will be 0, dp by p will be 0, ds by s will be 0. If there is no change, then I do not need to discuss any of this. That is what it is saying. Okay, we will consider there is always change. There is no du equal to 0 case. Now if I think about m less than 1, this is negative, and m is less than 1, this is positive. So I am going to get ds greater than 0, and the other one will be less than 0. So here this is not possible and this is possible. Only ds greater than 0 are possible. So now I am finally seeing that if my Mach number is less than 1, wait, I am having something wrong somewhere. What is wrong? I did the whole thing wrong. Where is it wrong? du greater than 0.
So du is positive.
M less than 1, ds is positive. Oh, I did the whole thing wrong, and you should have stopped me much before. You are stopping very late. Okay, finally, yeah. Anyway, we are going back to this whole thing. Whatever inequalities I wrote, everything is wrong. If m is less than 1, then this is positive. ds greater than 0, so this is greater than 0. This is less than 0, and so this is less than 0. This is greater than 0. This is what it should be. I just realized it did not match what I believe in Fano flow. So now I am right. Okay. We leave it like this. So we are finding that du greater than 0, that is I am going to have increase in velocity if my Mach number is less than 1. If my Mach number is more than 1, I cannot have increase in velocity. Okay. So this is not possible, this is possible. When my Mach number is less than 1, I cannot have decrease in velocity. I can have only increase in velocity. Only when I can have decrease in velocity only when Mach number is more than 1. Okay. These are the two things we are saying, which means I want to look at it in terms of dm by m also. Okay, where is my dm by m formula? Dm by m du by u into 1 plus gamma minus 1 by 2 m square. If I look at it like this term is not going to be ever negative. Okay, it is 1 plus something, and gamma is always more than 1, it will never be negative. Okay, which means whatever is the change in u is the change in m. Now I will tell this also means that dm less than 0, this means that dm greater than 0. That is, if I see that my Mach number is less than 1, it can only increase Mach number. If my Mach number is more than 1, I will first remove the cases which are, I will just underline the cases which are possible in nature. Only these two are possible in nature. If I think about Mach number greater than 1, it can only decrease. If my Mach number is less than 1, it can only increase. dm is greater than 0, can only increase, which means my flow has a general tendency due to friction that it will always go towards m equal to 1. Okay, that is the common thing you need to think about. My flow has a tendency to go to m equal to 1 naturally. Okay, m equal to 1 is a special situation like this. Okay. Now in this whole analysis, did I ever say anywhere that friction is so much? This whole analysis, whatever we did till now up to entropy, I did not use my momentum equation at all. Okay. But I got to a point which is possible, which is not possible and all. Am I doing something wrong somewhere? Not really, because there is a connection between, I go back to this momentum equation. Okay, I can replace this dp in terms of du, finally I will find that dx dictates du. I do not know what my du is as of now. Okay, that is given only by dx and my tau wall, the shear stress at the wall. Those are the things that decide it. As of now, it looks like I can find all variables just from looking at this. I cannot find any variable unless my dx is given, because I need the value of du to tell the new value of velocity. Okay, I can just tell the trend, the general trend, but I cannot tell anything specific. Okay. It so happens that the equations seem to be almost coupled, they are all independent equations. If you go look at it, we had 6 equations and 6 unknowns. Okay. Mass, momentum, energy, state, entropy and Mach number definition. These are your 6 equations in 6 unknowns. What are the unknowns? Pressure, density, temperature, velocity, Mach number and entropy. Those are your 6 variables. Okay. So you need all of them to actually solve the problem. Now the only thing left is to solve the problem, I need to find du, that is where my dx comes in. So I will go back and look at my momentum equation. Since I have it on the board, I will start from there. I will start from here. Now I will define one new parameter called friction factor. It is defined as tau wall, the shear stress, divided by dynamic pressure, half rho u square, standard aerodynamics based definition. Okay. If you use this definition, this particular f is actually called the fanning friction factor. Fanning friction factor. Okay. This is different from another friction factor used in incompressible flow world, people who are doing hydraulics. Okay, they have a different definition for this, and they call their f as fd. Actually I call their f as fd, which is actually Darcy's friction factor. Okay. The relation between f and fd is fd equal to 4f. Okay. That is the connection between these two. Okay. It so happens that the friction factor f is actually a function of Okay, it's actually a function of Reynolds number, the surface roughness of the wall with respect to hydraulic diameter. Epsilon is the surface roughness and it is normalized by hydraulic diameter, and the Mach number. Okay. It so happens that this function is not very strong function of Mach number, it is extremely weak function of Mach number. So what we will say is, I will use the charts used by incompressible flow people, because Mach number is not very serious function, my f value will not be very much off. So I am going to say I will use this friction factor, Darcy's friction factor. Typically in all incompressible flow books, they will give you something called a Moody chart. Moody most likely is somebody else, I do not know his history right now, mostly somebody else who actually gave it in a plot form. Okay. And incompressible flow people have given an expression for this FD. Okay, there are 2-3 formulas, they are all called Colebrook formula, there are 2-3 versions of it, whichever one you want to use you can use, they will all give roughly the same curve, there will be small this way that way variations, they will all be giving the same thing. In fact, the Moody chart is a plot of that Colebrook formula. Okay. It so happens that it is an implicit function. Okay, the function looks like this. I will just write the function here, 1 by f power half is equal to minus 2 log to the base 10 of epsilon by dh divided by 3.7, do not ask me why, it is just a correlation, plus 2.51, I do not think it is a correlation, maybe they did something else which I do not know about, times f power half again. Okay. Where this Reynolds number I will write here is based on hydraulic diameter and viscosity of fluid, u dh by nu, where nu is your dynamic viscosity, is that right? I think it is dynamic viscosity or kinematic, I just get confused with that. Dynamic I think is correct, kinematic I think is mu, is that the other way? This is kinematic, okay, so this is kinematic viscosity and mu is where without the rho is dynamic viscosity, okay. So anyways, so you can write it like this. Now if I look at the plot of this, it is going to, you would have seen Moody chart anyway, I will just draw the plot here, we have only 1 or 2 minutes, we will not go any more than this. If I draw a plot of this Moody chart, I did not want to put a Moody chart up for you guys, you can go find this, it is actually a log plot, it is friction factor F versus Reynolds number. For Reynolds numbers less than 2000 or 2300, the transition for a tube, it will just go straight like this, and suddenly it will go up after transition because turbulence increases friction, and it is going to go down something like this, and depending on various values of epsilon by d can be any of these curves, each of them is one particular epsilon by d. Okay. I am just drawing qualitatively, this is a log plot, okay, both are log axis, and this particular curve is 64 by Re. If I write it as 64 by Re, I am thinking about Darcy friction factor. There are some books which will give you 16 by Re, they are talking about fanning friction factor defined the aerodynamics way, that is what it will be. Okay. So depending on which book you are talking about, it will change slightly, just get used to this. Okay. Now after this we have to just go substitute this f into the momentum equation, and I think we will do that next class, we won't do that, it will take some time, I have to rearrange the terms and get it to a nice form, that will take a little bit longer. Since the class time ended today, we will stop here. Yeah, we will get back to that next class. Yes?
Is that ds by s?
No, it is just ds, it is not ds by s. Is it ds by s? It is just ds because it is having units of r. It is just ds. That is what it is supposed to be here. It is just ds. ds is same units as r. So it is going to be that. If you want, you can make it ds by r and it will become non-dimensionless automatically. Yes.
This have anything to do with the skin friction coefficient which we use in aerodynamics?
This f is somewhat related to the skin friction coefficient which you use in aerodynamics. It's coming from there, that kind of definition. Any other questions? Okay, we'll see you people next class.